Welcome to this video on scaling your database workloads on Exadata Database Cloud Customer. In this session, I'm going to cover a quick overview of some of the components and concepts. Then I'll cover how to size VM clusters and the reasons why you might want to change their sizes, talk about VM cluster node subsetting, and then go into the various ways we can scale, covering manual, automated, and dynamic scaling. And then finally a section on autonomous database scaling. So Virtual Machine Cluster, or VM Cluster, provides the link between the Oracle Exadata Database service on your infrastructure and the Oracle databases that you deploy. Each VM cluster needs a cluster network defined, and these provide isolation at the network layers. So in this example here, we have an Exadata Cloud Customer infrastructure with 4 database servers, giving a total of 760 cores and just over 5.5 terabytes of memory that can be allocated to run your Oracle databases. We also have 4 storage servers, giving 320 terabytes of usable storage. So here we've created our first VM cluster, and we've allocated 4 OCPUs or cores to each of 4 VMs. And you can see we have 1 VM running on each database server. So this VM cluster has 16 OCPUs to run the Oracle database workloads. Now we can create multiple VM clusters, and the second one we've created here is only running VMs on 2 of the database nodes, but each are running with 8 OCPUs. So again, we have a total of 16 OCPUs for the database workloads. Now the third example is where we only have 1 VM running, this time with 5 OCPUs. Now of course, having only 1 VM running means this VM cluster won't be highly available, but it might be suitable for test or dev environments, or where we're not running Oracle RAC across multiple database servers. And finally, we have an example of a VM cluster that can run the autonomous database. Now this needs to be in its own cluster, and this is how we run both autonomous and non-autonomous workloads on a single Exadata Cloud Customer. And for autonomous, there's an option to use a new metric for CPU resource allocation called eCPUs, which allow for more flexible use of resources. So let's look at some of the reasons for needing multiple VM clusters. Now, probably the main reason is around resource isolation. So as the VM cluster gives you your own dedicated CPU, memory, and storage to a given set of workload. It also gives you network security separation, allowing you to have different network segmentations and VLANs. And similarly, you can have different administrators for each VM cluster, giving you the ability to have different business units that are separate and isolated and are run and managed by separate teams. Now, you might have workloads that require maintenance schedules to happen at different times, and the use of multiple VM clusters allows this. And finally, you may want to run autonomous database as well as the regular database service. Now, with a VM cluster, it's important to remember that the database service that you consume is built on the allocation of OCPUs to the VM. Now, typically you want to consolidate multiple Oracle databases into VM clusters to get the most efficient use of the resources and smooth out the peaks and troughs of the workloads. So you want to size your VM cluster to meet the workloads whilst also keeping the costs down. Now, there's a minimum of 2 OCPUs per VM, which is to run the VM and the grid infrastructure software. And the VMs are symmetrical, so you have to have the same number of OCPUs in each VM within the cluster. Now, we support up to 8 VMs per physical database server, and that allows a maximum of 12 VM clusters with 2 database servers, and a maximum of 24 VM clusters with 3 or more database servers. But bear in mind, to reach those numbers, you'll need to have a number of single node clusters. Now, as I said earlier, the costs are determined by the number of OCPUs allocated, and the billing starts at the provisioning of the VM cluster and continues until the OCPUs are set to 0. So even if you shut down your VMs and then shut down your VM cluster, the billing continues until the OCPUs are set to 0. Now, when you do set them to 0, all the VMs in the VM cluster will be shut down gracefully, and billing stops. Now you might choose to do this when setting up a VM cluster to be used in the future. So configure it how you want it to be, but then set OCPUs to 0. So the VM cluster will be created, set up, but then shut down, and no billing will occur until you change the OCPUs to the required size. It's important for cost control purposes to correctly size your VM clusters. And during the sales cycle, we probably went through a sizing exercise to look at the workload over the previous 12 months to work out where the peaks were and whether there's any trends. Now, in this example, we've established that the peak usage requires 35 OCPUs, which is denoted by the red line here. Now, to meet that workload, we could create a VM cluster with 36 OCPUs, but for most of the time, you wouldn't be using all of those OCPUs. So instead, we might pick a lower percentile figure, maybe the 95th percentile, which in this case only required 22 OCPUs. So why might you actually want to change the sizing? Well, bear in mind that the sizing was based on historical data. So all we can do is look back and say, well, how was your workload over the last 12 months? What we don't know is, has the workload changed or is predicted to change? Also, maybe you need to create a new test or dev environment. Maybe it's the first time you moved your workload to an Exadata platform, and maybe you got performance different to what was expected, hopefully better. You may actually need to change the size of some VM clusters just to move things around or to create new ones. Or you want to try out the autonomous database. But another reason is in the case of failure scenario. So if you've got a 2-node rack cluster and one of the database nodes has stopped working, you may want to ramp up the resources in the remaining node to give you enough capacity to run the workload. And because billing is based on the number of OCPUs in the VM cluster, what options do you have for changing the size? Well, one is you can change the number of VMs in a VM cluster, and secondly, you could change the number of OCPUs in each of those VMs. So let's just go back to how we would initially provision a VM cluster. So first of all, you give it a name, a network, you choose the version of the grid infrastructure you want to run, and then you select the memory and the CPUs. And here we're selecting 2 CPUs per VM. And we can see here in the read-only section that it's 4. And the reason for that is that we have 2 database nodes, each with 2 OCPUs. And also we have 30 gigabytes of memory per VM, giving us a total of 60 gigabytes for the entire VM cluster. Now we also specify the local storage. So this is the storage on each of the database nodes, which is used for home and the U02 file system, etc. And then finally, we decide how much ASM storage to be assigned to the VM cluster. And this is the actual data where your databases are stored. So there's a minimum of 2 terabytes, and they'll tell you how much available storage is left. Now, at this point, you can also choose to allocate storage for Exadata sparse snapshots, which gives you the ability to take snapshots of databases to use for test or dev. And you can also allocate storage for local backups. Now, when you select either of these, this will change the ratio of how much storage you have available for data versus recovery versus the sparse snapshots. It's also important to remember that you cannot change these once you've created the VM cluster without actually recreating it. So we have this concept within Exadata Cloud Customer called VM cluster node subsetting. And this basically allows us to create a VM cluster on just a subset of the available database servers. And we can expand and trigger these clusters on demand. So in this example, again, we've got 4 physical database servers. And here we've decided to create a cluster on just 3 of those database servers. And this enables us to create the right size of VM cluster for the workloads to run. It also enables efficient sharing of the Exadata resources and allows you to only pay for the CPUs on that subset of VMs. So it gives you an element of cost control. So to provision a VM cluster on a subset of the database nodes, simply select from the list of available database servers, so which ones you want to use. So here we've decided to use 2 of the database servers and 2 OCPUs for each VM and 30 gigs of memory. So we end up with a 2-node cluster looking like this. Now here we have another example where we're going to expand a VM cluster. So using VM cluster number 3, which has VMs currently on database servers 1 and 2. And this selection panel, we're going to add VMs on the 3rd and 4th database server. So after we've done that, we end up with a 4-node cluster. And again, each VM added has the same number of OCPUs and memory per VM as before because of the requirement for symmetry. And we also have the ability to remove a VM from the VM cluster to shrink it. So in this case, we're going to select database server 3 to be removed. And then we end up with the remaining 3-node cluster. So let's talk about some of the limits and also the impact of when you do a scaling operation. So for CPUs, each VM has a minimum of 2 to run the VM software and the grid infrastructure, and you can increment by 1. Scaling this up or down doesn't require a reboot, but typically takes somewhere between 2 or 4 minutes to take effect. Setting the OCPUs to 0 is the way to stop billing on that VM cluster. So memory requires a minimum of 1 gigabyte and increments in 1 gigabyte units. And a change does require a rolling restart, as it does for changing the local storage. However, the database storage can be resized without any restarts. So what options do we have for scaling? Well, the first option is, well, no scaling at all. And this is really just a static, set it once and forget about it. So this is obviously the simplest to manage because you set it up and then don't really have to worry about it. So generally you would set it up to meet the peaks of your workload, which is the red line in the workload graph shown here. Now, there's 2 downsides to this approach. One of which is, well, you may not actually know where the peaks is going to be because all you know so far is the historical data and you could miss the future peaks. And the second downside is the fact you'll be paying for that red line all of the time, even when the workload doesn't require it. So this probably isn't the most efficient way to run it unless the workload is very static. Now, at any time, you can manually scale the VM clusters. So you might decide to change it manually on Friday evening to drop it down because the workload of the weekend is going to be lower. And then on Sunday, come back in and set it up manually for the week ahead. But that's probably something you not really want to do on a regular basis because it requires manual intervention. However, you can automate this using a simple cron job or bash script to call the OCI CLI to do this for you. And you could do that on specific days of the week or certain times of the day. And then finally, we have something called dynamic scaling, which we're going to go into a lot more detail, which is a suite of tools available for you to get the system to actually dynamically scale for you, either up or down, depending on your workloads. So let's go into those 3 options, but let's cover manual scaling first. So how do we change resources that are allocated to an existing VM? So on the service console in your OCI tenancy, go to the cluster details and choose the option to scale the VM cluster. So we'll display the current resources. It will show how many OCPUs, memory, and local storage. And you just simply move the sliders along to what's required. So the screenshot will show you how many VMs you have. And here we have a 3-node cluster with 5 OCPUs in each VM. And the read-only section here is for information purposes to tell you the total number of OCPUs, memory, and storage allocated to the entire VM cluster. So, and from here, you can stop a running VM cluster by scaling it down to 0. And when you do that, the VMs will be stopped in a graceful manner and the billing will also stop. And at any time, you can just restart it by setting the OCPUs to a minimum of 2 per VM. Now, the other reason for manual scaling is if you lose the persistent tunnel connection from the Exadata machine in your data center to the OCI tenancy in Oracle's data center, then you have the ability to scale resources using the console. So there's a command line interface called ODyS CLI, and you need to be connected to the guest VMs as root. And then once you've applied the command in one VM, it applies it to all of the nodes that the VM cluster node belongs to. So this example here, we're scaling down the number of OCPUs down to 2, and we can also send a message. And after we've done that, we can issue the scale get status command, and this will give us an up-to-date status of exactly where in the process we are with that scaling. So let's move on to automated scaling. So this is just taking the manual scaling commands and putting it into a cron job or a bash script. So you can either use the OCI CLI, and here we do a VM cluster update. We're setting the core count to 8 OCPUs, and also there's a link to the documentation there. Alternatively, you can use a REST API call to do exactly the same thing. And as before, we're going to set the CPU count to 8 for each of the VMs, and you can put these commands in a cron job or bash script. So let's move on to the dynamic scaling. So the nice set of tools that are provided in the MOS note listed here, and these enable you to automate the scaling up or down based on the CPU load or on a schedule. So there's a number of components to this suite of tools. One is the actual scaling engine itself, and then there's a remote plugin. There's also a chart maker, which can produce nice graphs on the scaling and what your workloads will look like. And then there's 3 separate plugins if you want to automate this using either Docker, Kubernetes, or Podman. So how does this work? Well, you can scale up or scale down the number of OCPUs based on the load or on a scheduling window. So this helps to reduce the frequent manual resizing if your workload's changing constantly. But you don't want to be going in and manually resizing and trying to catch up because you'll always be behind on the sizing. And it allows you to efficiently react to any spikes in CPU consumption on the clusters. So the way it works is there's a plugin that runs as a daemon, and you have a choice as to where you want to configure that. So the server it runs on requires internet connectivity back to OCI because it needs to use the REST API calls. So this server can be either one of the VM cluster nodes or an external server. And it'll monitor the CPU load on the DB servers, and we provide a standard CPU load tool to measure that. Or you can write your own tool if you have a different way of wanting to measuring things. So here's an example of where we're scaling on load. So if the load goes above a maximum threshold for an interval of time, it will automatically scale up the OCPUs with the option to ramp up faster if multiple scaling operations are required. And we keep increasing the OCPUs until we reach the maximum number that we've defined. So putting this into a real-world example, we might say if the load goes above 80% for a period of 3 minutes, we'll automatically scale the OCPUs up by a factor of 2 until we reach the maximum of 32. Now, the default period of measurement is 180 seconds or 3 minutes. So if the load has gone above 80% for 3 minutes, you can automatically scale up by 2 OCPUs. Now, bear in mind, if the peak has suddenly gone up really fast, increasing by 2 OCPUs, it might mean you still haven't got enough OCPUs to meet that peak. So this is where the incremental option comes in. And this basically allows us to say, okay, the first time we scale, we're going to add 2 OCPUs, but the next time we're going to add 4 OCPUs. So it ramps up faster each time. And the idea is we don't have to go through quite as many scaling operations to reach the required amount. And similarly, if the load goes below, say, 50% for a period of 5 minutes, then we'll scale down until we reach the minimum number of OCPUs that we've determined. And these can all be enabled and disabled at any time, and they're compatible with manual resizing. So here's some of the defaults for some of the options. So the default upper OCPU limit is basically as many OCPUs as you have available. And the default lower limit is 4 OCPUs per VM. The default scale factor is based on the number of database server nodes, and the standard measurement period is 180 seconds. And at any time, you can just execute the command with the dry run option that will execute the dynamic scaling scripts, but without actually performing the scaling. So you can look at the messages just to make sure it's doing what you expect it to do. Now, whilst we immediately scale up the OCPUs in the event the workload increases, we don't immediately scale down the OCPU should it drop below the target range. And the reason for that is we want to avoid a constant ping-ponging where we increase, we wait a bit, and then we decrease only to find we then need to increase it again. Because all these little scaling operations take a little while to perform. So by doing that, we're likely to miss the peaks. So instead, we'll wait for 60 minutes before lowering the OCPUs. Now, this delay only takes effect once the CPU utilization has stabilized into the target range. So in the diagram here, we have the initial scale up, And then once it's stabilized, we'll wait for 60 minutes before we begin any scale down operation. But we can have multiple scale down operations and we can do those at any time until we have the next scale up. Then we'll have another 60-minute period before the next scale down. So as well as scaling on load, you can also scale on schedule. So you can have a weekly based schedule. And in this example here, we're saying between Monday, between the hours of midnight and 8:59, we'll have 2 OCPUs. And then between 9 o'clock and 6 o'clock, we'll have 26 OCPUs. And you can have multiple lines for different time periods during the same day. And if we know Saturday and Sunday is going to be really low, then we can set it just to the minimum of 2 OCPUs. Now, in addition to the weekly schedule, you can also do a long-term schedule. And this is based on days of the year. So in this case here, we're expecting Easter, Black Friday, and Christmas to be really busy. So we'll set the OCPUs high. But equally, we know we have one quiet day a year where we're going to ramp it down. So let's now talk about how we actually implement this. On the left-hand side, we have our Exadata machine inside your data center. And on the right-hand side, we have the OCI tenancy located in the Oracle Cloud. Now, in this example, we're running the daemon directly on the VM cluster node. So in the event of either a schedule or load-based activity where we need to scale, the plugin will make a REST API call to the Oracle notification service. This will update the database control plane and send the acknowledgement change to the control plane server in the data center. And that will actually perform the operation to scale the VM cluster to the correct number of OCPUs. The second option is where the agent is now running on a separate physical server outside of the Exadata. Now, both methods work very similar, but because you need to have OCI connectivity from the server to OCI, you can choose the best place to run that, whether it's on the VM cluster nodes or on a separate physical server. So what we've covered so far is the Exadata database service. Now, one of the nice things about Exadata Cloud Customer is that we can run the autonomous database as well on the same infrastructure. So we're going to now look at how we scale the workloads with an autonomous database because it is slightly different. So let's start with how the various components interact with each other. So again, we have the concept of clusters, but in this case, we call them autonomous VM clusters or AVM clusters. Now, for each cluster, we're going to define a number of CPUs, a fixed ratio of memory for each CPU, and the maximum number of container databases, and also the storage. So within each cluster, you can create one or more autonomous container databases. And in each of these, you can create one or more autonomous databases. So for each autonomous database, you can also choose the number of CPUs, the storage, and whether you want to use auto-scaling or not. So the reason for requiring multiple AVM clusters are similar to before, but there are specific autonomous reasons like different compute models. As with autonomous, we have two different ways of charging, the traditional OCPUs and also the newer eCPUs, which is going to give you a lot more flexibility and should give you better granularity of your costs going forward. So different AVM clusters could have different compute models. Also, you may want to create and test data guard between AVMs, and this is a nice way of testing that. Now, the important difference with autonomous VM clusters is that the database service is built on the CPU resources consumed by the database and not the AVM cluster. Now, if you remember on the non-autonomous VM clusters, as soon as you allocate OCPUs to it, you're charged for that cluster, regardless of how busy the databases are. But with autonomous, you're only billed on the resources once they're consumed by a running database. So when you configure the AVM cluster, you set the CPU count for each individual VM, and here the minimum value is 5 OCPUs or 20 eCPUs with the new compute model. Now, for memory, the important thing to remember is that you specify the memory and it's a fixed ratio for the entire VM cluster. So you allocate the amount of memory per CPU, and then you want to scale the memory, you have to scale the CPUs. Now you select the maximum number of autonomous container databases as well for each VM cluster, and the creation of the autonomous container database requires either 2 OCPUs or 8 CPUs, eCPUs per node, with a maximum of 16 container databases per VM cluster. And finally, you define the amount of local storage and the database storage similar to before. So because there is a fixed ratio between CPU and memory for the AVM cluster, if you want to allocate more memory, you need to allocate more CPUs to achieve that. Now you can scale the CPU count per VM, and you can scale the maximum number of autonomous container databases within the VM, and also the database storage. However, note that changing either the CPU count per VM or the maximum number of autonomous container databases will trigger a rolling restart. Now your database services will continue to run while these updates happen in the background. Now, as well as scaling the clusters, you can also scale the individual autonomous databases. So here you select the number of OCPUs for your database from the list of all provisional CPUs that are available in that VM cluster. Now, also with autonomous, you can select a fraction of an OCPU, which will be useful if you have a number of very small databases that don't require a full core to run. And this CPU over provisioning will allow you to run more databases on your infrastructure. Now, one of the key differences for autonomous is you can set up auto-scaling for the autonomous database. And this permits the autonomous database to automatically use up to 3 times the amount of CPUs or storage if the workload on the database increases. And we'll see why that's very beneficial from a cost point of view in a couple of slides' time. Now, with autonomous, you set a CPU count for the database, and then with auto scaling switched on, it can automatically scale up to 3 times to meet any workload changes, and will also scale back down automatically. So here the CPU count is set to 4, and we can scale up to 12. So when scaling up, you're only charged for the fractions of the OCPUs for the time that you're using it. So unlike the traditional VM cluster, where if you needed 12 OCPUs to run all the workloads, you'd be paying 12 all of the time without any scaling. With autonomous, it's doing that scaling for you automatically. And as a reminder, with autonomous, you're not billed on the allocation of CPUs to the cluster, and you're not billed at the creation of the autonomous cluster databases, but only when the database is running. So these changes, plus the use of auto-scaling, can reduce the cost of running your Oracle databases. So let's look at a typical workload and see what difference it makes. So here we've set the configured CPUs to 10, and obviously with auto-scaling, you can then use up to 30 CPUs. Now, as the workload changes over time, you're being billed for the 10 configured CPUs, but when you need more, as shown by the red line of the workload, you're billed for the fractions of the CPUs for the time it's needed and no more. So this can have a dramatic effect on your billing. Now this shows the workload during the day, but if we know the workload is going to be quieter at night, we can change the configured CPUs down to 5, and the auto-scaling limit will now be changed to 15. And now we're lowering the billing costs even further. So in this video, we've covered the various components that make up the environments in which to run your Oracle databases, and shown how you can use scaling, whether manually, automated, or dynamic, to help control your costs. And finally, we covered the differences with autonomous and how using this can give you further control over your usage and costs. I hope you found this useful, and thank you for watching.